concerning the energetic analysis of the Hirn cycle with extractions, we first need to look at what is going on when two different flows are mixed. That's happening at three different locations in this cycle. Each time the flow that is extracted from the turbine is mixed with the other flow that is going out of the pump. So let's take as an example for the mixing balance what's happening when the flow from the first extraction S1 is mixed with the flow from D1, so out of the first pump, and both of these flows are mixed, and the state of the mixture is called point C2 in the example. So first we can do a mass balance because of course the mass of the mixture is equal to the sum of the mass of both products that are mixing. But then we can also do an enthalpy balance. This is just the first principle of thermodynamics. If we do just a mixture, there's conservation of the enthalpy. And when we say conservation of the enthalpy, because we have different mass flow rates, we don't just have a conservation of the specific enthalpy, but of the enthalpy flows. So the mass flow rate of enthalpy coming from D1 and the one coming from S1 are equal to the enthalpy flow rate that is going out of the mixture, so with the mixing state C2. And if we blend these two balances, we can express the specific enthalpy of the mixture C2 as being an average of the specific enthalpy of D1 and S1 weighted by the mass flow rate ratio that are respective to these 2 points. So that's how to calculate the specific enthalpy of the mixture. Then concerning the whole cycle and the changes in the cycle efficiency we have. For the cycle efficiency, we know that we have decreased the heat transfer with the hot source, because now concerning the heat transfer with the hot source, we only need to heat up from D4 instead of D1 up to A. But we also have changed the technical work or technical power that is exchanged between the fluid and the moving parts inside the turbine. This is due to the fact that the extractions have decreased the mass flow rate that is expanded, so not all the mass flow rate entering the turbine is expanded down to the low pressure of the cycle. So one elegant way of writing this is to write that so here it's the absolute value to have something positive, the technical power of the cycle. So here we take into account only what is exchanged in the turbine, because we can neglect the technical work of the pump. It's equal to here the technical power that would be obtained if all the mass flow rate MA entering the turbine was expanded from inlet A to outlet B, minus the decrease of technical work that is due to the extracted mass flow rate, so minus the sum of the mass flow rate of each extraction multiplied by the difference of enthalpy remaining between the enthalpy of the given extraction and the outlet enthalpy of the of the turbine. So this way we can see in this term exactly what is the decrease in technical power that is induced by the extractions. This means that for a given technical power that we want for a turbine, if we perform extraction, we would need also a bigger turbine, and a bigger turbine means also a higher investment price. So now that it's properly defined, the technical power of the turbine, then the efficiency of the cycle is still the same. It's the ratio between the absolute value of this technical power divided by the heat that needs to be exchanged and paid in the vapor generator.